the stream. We are starting to record. We got good audio and we should be good to go. And this should come up in just a second. Yep, we have a stream. Okay. So I'm just going to wait for people to get in, and if I wasn't lazy, I would edit this out, but I am, so I'm not going to. Yep, so I'm going to come over here and pull up homework. Oh, damn it. Why is it doing this? It never does this. Okay. Well, let's see if I can troubleshoot this real fast. Just 1 second. So I see some people are coming in. My camera just keeps switching to standby mode, and I'm not quite sure why, so I'm going to try to figure that out. But in the meantime, go ahead and look at some questions that you'd like me to answer. What I'm going to do is I'm going to go over the homework from last night, and then I'm going to do an example of a charge that's spread over the arc of a circle. How to turn off demo mode. That sounds like it. That's not the camera that I have, but this might give me some idea. So, it doesn't do this when I have a memory card in. But anyway, I guess I'll just fix this if it switches over, and I'll try to pay attention. Okay, so like I said, the first thing I'm going to do is I'm going to go over the homework. So this problem was a little bit more difficult than something I'd ask you, particularly because of where I'm asking you to find this force at. And the thing that's kind of unique about this problem that we hadn't seen to this point is that I'm spreading this charge here. So this was the lambda as a function of y that ended up being that really ugly function that I had given you. But for us, I'm just going to treat it as lambda as a function of y. That doesn't really change anything. But what made this problem kind of unique was the fact that the point where I'm finding the force, I said this was some q, I think was equal to 2q, but again, it doesn't really matter. I'll just do this in terms of capital Q. The thing that made this unique was the fact that this was kind of in the middle of the distribution. So when you're finding your r hat vector, it's going to change direction, so that for charges down here, it's going to point up here, and for charges up here, it's going to point down here. So that's kind of what made this a challenging problem. And I wouldn't really ask you something this difficult on the exam, but I did want to give you something as a challenge to work on. So ultimately, what we're going to see here is if we're careful with the way that we do this, the way that we're parameterizing this r hat vector will be the same for both of these cases. So in order to show you how I'm going to do that, let me redraw this so I have a little bit more room. So I'm going to move the dq that I'm talking about down a little bit. So the dq that I'm going to talk about, I'm going to put like right about here, and then here's my point a comma minus a here with my charge q. So this is what my r hat vector looks like. Okay. Now, this is going to be the distance r. We know that this distance is going to be a. This is the distance y. And so what we can do is we can fill in a triangle here by drawing this horizontal line. So this distance here is also a. And since this distance is a, this distance is y, this distance here is going to be a distance of a minus y. Okay? And so when we're looking at this triangle right here that I have drawn, then we see that this r is just going to be equal to the square root of a squared plus a minus y squared. Okay? So that was the first important thing, to be able to identify this a minus y piece over here. Now, the next thing that we can do is we can look at what the unit vector r hat is if we draw some angle theta in here. So let me just write the general equation so you remember where we're trying to go here. So that's to say that df is going to be equal to 1 over 4 pi epsilon naught q dq divided by r squared times r hat. So we've already determined what r is, and while we're at it, let's go ahead and write down what dq is. So in general, dq is going to be lambda dl. We see that our charge is spread along the y-axis, and so dl is going to be equal to dy, and lambda is some function of y that I gave you. So the last thing that we need here is to figure out what r hat is. So now that I've drawn in these angles here and here, what I can do is I can say that r hat is going to be equal to some amount in x hat plus some amount in y hat. So for this r hat that I have here, this is going to be positive in x, right, because this portion is going to be positive, and negative in y. So really, I would have a minus sign here. And then I can figure out which trigonometric ratio I want for the x portion and the y portion by seeing where my adjacent and my opposite side are. So this portion, which is a portion in x, is going to be the adjacent side, and so this is a cosine of theta. And this portion here is the portion in y, which is the opposite, and so this is going to be sine of theta. Okay? So now, when I look at this and I plug in cosine of theta and sine of theta in here, we're almost there, but remember, we don't have theta as some parameter that's given, or we're not integrating over theta. Fuck. You didn't hear that. All right, I'm back. We're not integrating over theta, so we're not going to be able to eliminate it. So what we need to do is we need to reparameterize cosine of theta and sine of theta in terms of the things that we can integrate over, so that would be y. Okay, so what that means here is that this cosine of theta is going to become an a over r, right, because this is the adjacent, and then this is r, so this is a over r x hat. And our sine of theta is going to become a minus y divided by r times y hat. Okay, so now let's pause here for a second, because I said if we were careful here, when we do the rest of this, when we do the bottom part, what we have here is going to give us the behavior that we need. And in order to see that that's true, what we can do is we can consider what the range of y is. So y is going to start at 0 up here, and it's going to go to a, and then it's going to go to minus 2. Or at its range, it's going to have values that are larger than a. So what that means here is that if y is smaller than a, so if y is smaller than a, then this numerator is going to be positive. And so if the numerator is positive, I'm multiplying it by a negative sign. That's going to give me the behavior that I want here, right? But if y is going to be larger than a in a magnitude, so if y is larger than a, that means that a minus y is going to be less than 1. And so what that means is I get a negative times a negative, and that makes this up here going to be positive. Okay? So we can see that for the entire range of values that we have here, this equation is actually going to give us the behavior that we want for the unit vector. We could also see that if we say that y is equal to a, then this is going to be 0. So when y is equal to a, so that's this point here, then what we see is that this is just going to point in the x direction. Again, when I'm at this point, that's what I should have. Okay. So the last thing that we need to do is put all of this together in our equation and set up the integral. And so when we do that, we say that f vector is going to be equal to 1 over 4 pi epsilon naught times the integral from the lower bound to the upper bound, so this is minus 2a to 0, of dq, which is lambda, so I have lambda as a function of y, times dy divided by r, which is going to be a squared plus a minus y quantity squared, but we're going to get another one of those from here, so this is actually going to be to the 3/2, times a x hat minus a minus y hat. And then that's it. Does it matter where you say where your R is? Capital R? No, I mean, so this R that we have is always going to be the hypotenuse of the triangle, and it's going to be changing as I'm sweeping through these values. So in a sense that it does matter where you say R is. It has to represent the distance from some dq to this point, but you could have used the one down here. I just made a choice for where I wanted to show where mine was. I chose it to be from here. You could choose it to be from here. But when you're thinking about how you parameterize this, the important thing is that R is representing the distance from the dq to the q. So it's probably not the type of answer that you really want me to give you, but it kind of depends. It's just something that you need to define, and you need to show some consistency. It's kind of the same way with theta. Theta is this internal parameter that I'm defining. I could have defined the angle phi here. That one's a little bit more arbitrary, because what that means is I can do this in terms of either one of these two angles. But it's something that you'll just define and then work the problem through with it. And as long as you're showing it in your diagram, that's the important part. Yeah. Yeah, and you guys are always free to. I'm reading chat as I'm doing this. So if you have questions, you can ask them. Okay. So let's go ahead and move on to the example from. The book that kind of led into our discussion today about how you can deal with arcs of charge. Okay. So in that example, what I had given was some arc of charge like this. And what we wanted to do is we wanted to find what the electric field is at this point. That works. I didn't know if it was better to have a point at the origin. Yeah, so you could do it from the origin. What I would say about that is I would be a little bit careful with using so. As long as you're understanding, and just to give you a different example, say this was what I was looking at. You could define the vector r this way, but you might inadvertently convince yourself that, say this is the point 0 a on this axis. If you defined it from the origin, you might be inclined to say that r is equal to a. And one of the values that r can have is a, But really, in this case, and this is kind of why I draw it a little bit in the middle, this is also R, and this is also R. All three of these are R. So for this example, this R is really equal to the square root of a squared plus x squared. And when you're at the origin, the R is equal to A. So that's it's okay to do that, to define your R coming from the origin, but I would be careful defining it at like extreme points, because you might be inclined to say, well, it's just this value. It is at that point, but it's not always that point. Okay. Yeah. So Rachel, the reason why it's not in the last example, R is equal to the square root of a squared plus a squared is almost like what Eric is asking, because when you look at this, the square root of a squared plus a squared is one of the values, or actually in this case it's two of the values that R has. So if this is minus 2a and this is a minus a, two of the values for R actually are a squared plus the square root of a squared plus a squared, right? Because I can look at this and I can say this is the square root of a squared plus a squared, and this is equal to the square root of a squared plus a squared, right? So those are values that R can have, but you have to take in consideration that there's a whole lot more R's than just the two that are at the endpoints. And so when you're looking at defining this, the R that you have always needs to take all of the information into account. And that's why what I did here was I said, well, this is some distance y, this is some distance a, this is then the distance a minus y. And so when you look at this, you end up recovering when y is equal to minus 2 and y is equal to, ooh, something's wrong here. Something's wrong here. Why is something wrong here? Oh, it's because the values of y are themselves negative. The values of y are themselves negative. This needs to be a plus y. This needs to be a plus y. Let me go back. I made a mistake. Yeah. I made a mistake. Because really it's like a minus y. Here's the minus 2a. This is a comma a. And then this is a distance y, but it is itself negative. So what that means is when I plug in values, as I'm looking at values for y here, because you could have y is equal to minus a over 2. Let's look at y is equal to, oh, sorry. Sorry. Yeah, these were the technical difficulties I was talking about. So I'll try to figure out why this is happening later, but I'm just going to roll with it. So if the screen goes out again, just try to remind me. Okay. So these values of y, this is the minus y-axis. This is the positive x-axis. And so these values of y, when I plug them in, are themselves negative, which means that this is still some distance as a magnitude of a distance of a. But really, when I'm looking at, say, this right here, so this is some dq, this is r, this is a, but this is really the value that we're interested in. This is itself minus y. This is minus y. And so this distance is going to be a minus y, which is really a plus y. Because if I take some value here, the values that I'm going to have are negative. So it would be like minus a over 2, for instance. So I could take this as an example. This would be minus a over 2. and then this is giving me the behavior that I need. So really, in my answer, what I need to have is I need to have r is equal to the square root of a squared plus a plus y squared, and r hat is equal to a over r x hat minus a plus y divided by r y hat. And like I said, this is more complicated than something I would ask you, partially because of these issues with negative signs. But the thing to take away from this, and to answer the questions that you guys are having from, let's refresh this so it doesn't do what it was doing before. To answer some of the questions that you guys were having about why isn't this r is equal to the square root of a squared plus a squared, that's because it's not always that distance, right? It varies, right? So at its two extrema, this is r is equal to the square root of a squared plus a squared, and this is r is equal to the square root of a squared plus a squared. But there are all of these intermediate values that it has, and at this point, this is actually r is equal to a. So you have to be careful with this like this, because r itself, r has to be a function of y ultimately. Because as I change y, r is going to change. So it can't just be r is equal to a squared plus a squared, precisely because it doesn't. This doesn't suit the entire distribution for all of these DQs. Two of them happen to have that r. One of them has an r that's r is equal to a. So you need to look at this as some function. So as you're changing y, r changes, and something that you can do when you're thinking about as this r is changing, you can write down what this r as a function of y is, and then ask yourself, when I plug in values for all of these points, does it give me the r that I expect for those points? Okay, so let's see if that's true here. So I know that this one should be r is equal to the square root of a squared plus a squared, and I know that this one should be r is equal to the square root of a squared plus a squared, and this one should be r is equal to a. So let's see what happens when I plug in values for y. So this one is at y is equal to 0. When r of y is equal to 0, when I evaluate this, this is going to be the square root of a squared plus a plus 0 squared. So this one is the square root of a squared plus a squared. So that's good. So we know that that one's good. Let's see this one. So for this one, this is the value where y is equal to minus a. So this one has y is equal to minus a. Let's see what happens when I plug in minus a into this one. So r as a function of y is equal to minus a is going to be equal to the square root, lose more chalk that way, is equal to the square root of a squared plus a plus negative a, quantity squared. This is 0. This is the square root of a, so this is equal to a. That one checks out. Okay. Let's see what happens when we plug in this one. So this is minus 2a. So for this one, what I'm going to have is r of y is equal to minus 2a is going to be equal to the square root of a squared plus a minus 2a squared. This is going to give me minus a squared. And so again, this is going to give me r is equal to the square root of a squared plus a squared. But these are only true for these boundaries, and we see that r is equal to a in the middle. That's ultimately the thing that you take away from this. And that process that I went through here, it's it's not something that we really teach. It's kind of hard to teach you how to do that. It's something that you pick up with time and solving a lot of problems. But when you run into these situations, and maybe I'm not sure if I have the right r, something that you can do is to go through this process and say, well, I know what r should be here, and I know what it should be here, I know what should be here. Let's see if that function actually matches what it should be at these points. And if it does, then you probably have the right r. Okay? Let me go back. I think there were a couple other questions. That works. I didn't know if it was better to have it pointed. Yeah, okay, I think I answered that. Would have been okay to take into account for changing y component in r hat by calculating in two different segments and combining them together. Yes, Brian, you could absolutely do that. And the reason why, it's something you probably learned in your calculus class, that and this gets a little muddy depending on the way that you're doing the integrals, but if I do something like the integral from a to b of x dx plus the integral from b to c of x dx, this is actually equal to the integral from a to c of x dx. And so yes, you can absolutely break this into multiple parts. Okay. All right. So now that I beat that one to death, I think we can move on to the next example. And like I said, this was I wrote in the notes that the problem that I came up with then was probably the worst problem that I could give you, but clearly I've come up with something worse. But like I said, I wouldn't ask you something this difficult on a test. Okay. So let's go back to. I think there was another question before I erase this. Is the charge distribution even in this case? If so, is it wrong to just... Remington, that's a very good question. So when you look at this, you say, based on this distribution, I know this part is going to be, this part has the same distance as this part. And so could I just... say, well, the x components from up here, or sorry, the y components from up here are just going to cancel the y components down here. In this case, you can't do that. And the reason why is because y as a function, lambda as a function of y was that terrible, messy thing that I gave you, and that undoubtedly is going to end up with more or less charge up here than down here. So the only time I would say that you should use symmetry arguments is when you know that there's the same amount of charge on this side and that it's spread in a symmetric way. Uniformly spread charges are an example of that, but you could come up with some function that would have the same charge up here and up here that is some function, but it's mirrored. So whatever the distribution of charge is up here, it's mirrored over here. And that's a case that you could say that there's no force in the y. But you can't say that in general because this lambda is a function of y. Were I to draw it pictorially how much charge there is here, like as like some wedge, I could have like all that charge up here, and then maybe I might have something like this, right? So I could have a lot more charge up top than I have at the bottom. So you can't say in general just because it exhibits some type of symmetry when it comes to the distances. So this distance was the same as this distance. It doesn't necessarily mean that you can just cancel the y components. But that's a good question. I wanted to know where we could find this equation since I did not see it in the notes. Oh, and homework 4, oh, sorry, I read the second one. Homework 4, question 4.2. So I haven't, yeah, Amir, I haven't finished those parts of the notes. I'm going to upload that tonight. Yeah, and like I said, I apologize, I'm a little bit behind. But those types of questions don't take a lot of time. Once I put that in there, I don't think it'll take you more than like 10 minutes to be able to do those questions. But I guess I could just go over that now. Man, this thing's the worst. You coming back? Okay. Yeah, I could just go over that now. But I don't know if I'd give you enough context. Let's just do it now. Okay. So those two equations that I'm talking about in the second part, or the second and third part of the homework, have to do with how you can go from some electric field to some electric potential. And to give you some context and to draw some parallels to some things that you saw last semester, this had to do with the work energy theorem and the potential energy function. So you remember, and I'll show you an example of this, that if I have some force and I want to find what some potential energy function is, the way that I can do that is I can say that U is going to be equal to, and in principle, this would be like a U as a function of some R vector. You know what, let's just leave the vector notation off for the time being. U is going to be equal to the negative integral of F vector dot dl. Okay. This came from the work energy theorem, and I'll give you an example of this in a second so you can see it in action. But if I instead had some potential energy function, I wanted to find some force from the potential energy function, what I could do is I could say that F vector is equal to the minus gradient of the potential energy function. Okay, where this gradient in Cartesian coordinates is x hat, partial derivative with respect to x, plus y hat, partial derivative with respect to y, plus z hat, partial derivative with respect to z. We probably won't see anything in 3 dimensions, but this is the general gradient vector in Cartesian coordinates. So right now it might just look like I'm writing down a bunch of equations, but let me show you 2 examples of how this works. So the first example is if I have some mass in the presence of gravity, and this is the only force acting on it. And what I'd like to do is I'd like to, it's getting blurry. Yeah, sorry, the autofocus gets off sometimes. Unfortunately, I just have to work with that. So if I have this mass that's in the presence of gravity, I can draw this Freebody diagram. And so this is just going to be the force. And if I say that this is the positive y direction, the force is going to be minus mg y hat. So what we'd like to do is we'd like to calculate what the potential energy is. And what we're going to get out of this is something that's very familiar to you. So in order to do that, what we want to do is we want to use this equation that says the potential energy is equal to the minus integral of F dot dl. So in order to use that equation, we know that this is the force. We know that we have some dl vector. Now we haven't seen dl vectors before. We've seen just dl's. Can I go back to the vector f part? Can you explain a little bit more what you mean, and then I'll come back. I'm not quite sure what you mean when you say the vector f part. I think you might mean this part, but you'll see how this works more when I'm using this this formula when I'm doing this example. So I have this f vector. I have this dl vector. Now dl vector is not something that we've used before. We've seen dl, but not a dl vector. And the important thing about dl vector is it's really the same thing as a dl, but it also has a direction that that goes with it. So this dl vector in this case is just going to be dl vector is equal to y hat dy. Because this is where I'm moving this charge, or sorry, this mass. I'm moving it up and down, ultimately. So when I plug this in and I evaluate this equation, this says that this is going to be equal to the integral of minus mg y hat dot y hat dy. Okay, so I have a negative sign out front. So y hat dot y hat is 1. Because any vector dotted with itself is just the magnitude of the vector squared. But this is these are unit vectors, so that's just 1. And then what I have is this is going to be the integral of mg dy. Now this is an integral any of us can do. It's just a constant, right? So this is just going to be equal to mg y. So what this says is for some mass in gravity close to Earth, the potential energy function is just mgy. Now, if this doesn't quite look familiar to you, it will if you use a slightly different notation and you call yh. So potential energy is mgh. Okay. So now to get to, God, this thing's the worst. Now to get to Eric's question. So Eric wants to know about this second part. What is this f vector is equal to minus grad u mean, or how do I use this? Well, this is how I can, if I give you some potential energy function, how I can figure out what the force is. Okay. So what we can do here is we can actually undo what we just did, because we integrated the force to get the potential energy. But we can go the other way, right? So if I want to recover what the force was acting on this particle, what I would do is I would say that F is equal to minus grad u, which is equal to minus grad vector. This is a vector, so this is minus grad mgy. And then look at what the gradient says. So the gradient's an operator in 3 dimensions, but there's no x dependency here, right? There's no z dependency. There's only y dependency. And so when I do that, this is going to become minus y hat partial derivative with respect to y of mgy. And any of us can take the derivative of just y with respect to y. That's just going to be 1. And so this gives me minus mgy hat. Okay. So this is how, and let me know if that doesn't quite answer your question. But this is how I can go from the force to the potential energy function, and from the potential energy function back to the force. And this might seem like I'm making a big deal out of nothing, or why would we do this in the first place? Well, remember back to last semester when we were doing problems with forces. The first way we did it was with kinematics. We could draw free body diagrams, and then we could say there's some sum of forces acting on this. This gives me an acceleration. If I have the acceleration and it's a constant acceleration or a time-dependent acceleration, I can find what the velocity is. I can find what the position is. And in doing all of that, I have to carry around all of these vectors. But we found there was actually a better way to deal with these things. In the case of constant forces anyway, that if I could find what the potential energy function is, I don't need to worry about the vectors. I still preserve all of the same information, but it's a lot more manageable for me to solve this problem if what I'm trying to do is find the velocity at the bottom. It's a lot more manageable for me to say that mgy is equal to 1/2 mv squared and solve for v than it is for me to write down the sum of forces, say that sum of forces is equal to the mass times acceleration, integrate the acceleration once to find the velocity, integrate the velocity once to find the position, say that the position, what is the time when the position is 0, plug that time back into the velocity equation. They end up being equivalent ways of approaching these problems, but the energy conservation way is, when available, is always the easier of the two, and it's important to be able to talk about physical systems in multiple equivalent ways. That's kind of like one of those things that I was talking about at the beginning of the semester. What is theory? Well, theory, you can come up with new ideas that can explain the same systems, and they're going to be equivalent. It's a very important tenet. Got it. Is this the reason why we're going versus other type of energy? So Eric, that's another good question, and that actually kind of leads me into the second example that I was going to do. So this was just the simplest example that I could think of. But another one that we could do is we could consider some spring, right? We know what the potential energy of a spring is. It's spring potential energy. So the potential energy of a spring, U as a function of x, is just going to be equal to 1/2 kx squared. Right. So this is something that we we should remember from last semester, and we might even remember what the force of a spring is, and know what that is offhand. But what we like to do is we like to show what it is based on these two relationships. And so if we want to find what the force acting on the spring is, we know what the potential energy function is. We just need to calculate the negative gradient of the potential energy. And so in this case, this is not dependent on y or z, so I only have the x portion. So this is equal to minus x hat, partial derivative with respect to x, of 1/2 kx squared. Again, this is a derivative that is pretty easy to take. Derivative of x squared is going to be 2x. That's going to cancel this 1/2 here. And then what we end up having in the end is this is minus kx x hat. So the force of a spring is equal to minus kx x hat. And this is what's called Hooke's law. Damn it. This thing, really? Okay. So the takeaway here is that there's two equivalent formulations of mechanics, right? There's the potential energy and conservation of energy formulation, and then there's the forces and kinematics formulation. And you might be wondering why I'm going through all this trouble going over old things. Well, I wanted to draw some parallels for things that you've seen already to lead into the equations that I'm going to talk about. And I'll write about them in more detail than we're going to talk about right now. But the takeaway is, and this I always think that these kinds of things are very beautiful because of the way that physics has two types of symmetries. It has physical symmetries, like you can say like the left is the same as the right, but there's also symmetries that come up in equations. This is an example of symmetries that come up in equations. So, to define the electric potential, we actually define it almost exactly the same way as the potential energy. And that's to say that the electric potential is equal to the negative integral of E dot dl. And to undo this, if I wanted to find what the electric field is given some electric potential, this is to say that E vector is going to be equal to minus grad V. And so, like I said, in physics there's two types of symmetry. One is the type of symmetry that comes up in physical systems. If I say that I have some charge distribution like this is symmetric across the y-axis. But there's also this type of symmetry in equations, when I can say that for the ways to formulate mechanics and the ways to formulate electricity and magnetism, I see these equivalencies coming up. So is it safe to say what doesn't cancel? Okay, yeah. So is it safe to say what doesn't cancel x, y, and z in the gradient part is the type of energy from the conservation of energy? So is it safe to say what doesn't cancel in the gradient part is the type of energy from the conservation of energy? I'm not quite sure how to answer that, because there is something else that I'm kind of sweeping under the table here a little bit, because you can calculate these potential energy functions, but that doesn't actually guarantee that that energy is conserved. And really, in order for energy to be conserved, and something that we're going to see when we talk about electrodynamics, is it's not enough to just be able to calculate some potential energy and throw it into some conservation equation and say potential energy that I calculated plus kinetic energy plus another term for potential energy plus kinetic energy, those are equal. They're not necessarily going to be. But the thing that will guarantee that that's true is if the integral around a closed loop of f dot dl is equal to 0. So this is to say that if I have some force and I bring it around some path, but I bring it all the way back. So this is to say, if I have this chalk, treat this as a mass. If I move it out, I move it up, I move it over, and I move it back down, and then I'm at the same point. If the integral of the forces around that path is equal to 0, then energy is conserved. But if that's not the case, then you can't say that energy is conserved. And we're actually going to see an equation, again, very much like this later in the semester when we're talking about circuits. I don't want to get into this too much, but this equation, it's actually one part of what's called Faraday's law. And if you've heard of Kirchhoff's loop rules, it's equivalent to that, only better, I think. Because of the way that and these are things that only people like me would actually care about. The way that the negative signs work out in this is consistent with Faraday's law. But Kirchhoff's loop rule is actually not like that. And I feel like I'm going off on a little bit of a tangent here to answer this question. So I want to come back and say, is it safe to say what doesn't cancel x, y, z in the gradient part is the type of energy from conservation of energy? So I think I think I'm getting at what you're asking. So no. So what it does tell you. So if I go back to this example with this this mass mg. If I go back to this mass mg, the fact that when I'm or better yet, if I talk about the potential energy, U is equal to mgy. When I look at this and I'm taking these partial derivatives, the fact that the partial derivative with respect to x and the partial derivative, ooh, who did that? Come on, you guys are supposed to keep me honest here. How long was that there? Anyway, it's okay. The fact that when I take this gradient of this, the fact that this and this don't act on it, just means that the force ultimately is in the y direction. That's what it means. It ultimately means the fact that there's no terms that are non-zero from this and this just mean that the force is in the y direction. Okay. So sorry if I kind of went on a different tangent over here, but ultimately these two equations again are things that we'll talk about later in the semester. Okay. So any questions about this? So when it comes to labeling this, you'll want to explain what this is, what this is, what that is, what this is, what this is, and what that is. But like I said, I kind of verbally explained it, but I'm going to be working on the notes tonight, and I'll have a better explanation of this when I do that. Okay. Okay. So let's go ahead and move on to the example that I had in the notes, because I think that'll help you with doing the other part of the homework. Okay. And if there are some questions that you have based on some of the classwork, because I didn't actually work those for you, but if you have questions about those, I can do some of those now too. Okay, let me reset this so that this doesn't crap out again. Okay. So the example that I had in the notes was this arc of a circle with some charge that was evenly spread here. I don't remember exactly what it was, but we can just call it some capital Q. And what we wanted to do is we wanted to find what the electric field at the origin was. Okay. So in order to do this, what we can do is we can define some dq here. We can draw the vector that points from dq to the origin. So this is just some r hat. This is some angle theta. This is some angle theta. And then we can write down the equation that we need. And actually, you should probably write the equation down first. So dE vector is equal to 1 over 4 pi epsilon naught dq over r squared times r hat. So we need to know dq, we need to know r squared, and we need to know r hat. So let's start with dq. So in general, dq is equal to lambda dl. And I also need to give this some radius. So this is going to be some radius of r. So first let's determine what lambda is. So lambda always is some charge per length. And so here what that means is we have some total charge q that's spread over half of the circle, right? So a whole circle has a total length or a circumference of 2 pi r. So half a circle is going to be half that. And so this total length of this is going to be pi times r. Okay. Now dl for the arc of a circle, and this is something that you can just hold on to and put in the back of your pocket. dl is just going to be r d theta. I won't really go into exactly why that is, but if you're interested, come talk to me. I'll explain why. So now what we can do is we can say that this is going to be equal to q divided by pi r d theta, or this is going to be equal to q divided by pi times d theta. Okay, so that gets us our dq. Now let's look at r. Well, for these problems, actually, r is probably the easiest thing here. For every point along this arc of the circle, the distance to the origin is the same. That's what defines a circle, right? So that says then that r is actually just capital R. Now let's look at r hat. This is the one that's tricky. So r hat, by definition, always points from dq to the point of observation. So it points from here to here, and I've actually already drawn it in here. So we know that this is going to have some part in x hat, and it's going to have some part in y hat. So completing this triangle here, we see that the adjacent side is going to be the x portion, so this is cosine of theta, and the opposite side is going to be sine of theta. And additionally, this is in the negative x, and this is the negative y. So this is going to be minus cosine of theta, and this is going to be minus sine of theta. Now, what you might be tempted to do at this point, because this is what we ended up having to do with all of the other r hats that we've dealt with some of the other problems, is to look at these and reparameterize them in terms of lengths, right? We would say, well, we can say, ooh, that was terrible. Need to cut my nails. So we could reparameterize these in terms of lengths, and so this is going to be some length of A, and this is going to be some length of B, so cosine of theta is equal to A divided by R. But that's actually not what we want to do in this case. And the reason we know that that's not what we want to do in this case is because of this. We know that we're integrating with respect to theta, and so we want these thetas to be here because when we do the integral, that's what's going to get rid of them. It's not the reparameterization that's going to do it for us. Okay. So let's plug everything in here and then turn the crank. And so what we see then is that E vector, need another piece of chalk. And I really wish there was a nice way that you could take all of these little like chalk nubs. I have like a whole bunch of these. I wish there was a way that you could combine them into one usable piece of chalk again. Okay, so E vector is going to be equal to 1 over 4 pi epsilon naught times the integral of, this is going to be lambda, which is going to be, well, it's this term here, so this is going to be q divided by pi times d theta divided by r squared times r hat. And so this is times minus cosine of theta x hat minus sine of theta y hat. Okay. Now the next thing that we want to do is we want to identify what the limits of integration are here. So where does this chart start and where does it end? Well, that has to do with the way that we define theta here. And so the way we define theta is that this is going to go from 0 and it's going to go all the way around to pi. So this goes from 0 to pi. Okay. So let's pull out some of the constants here and then do the integral. And so what we end up seeing here is this is going to be equal to q divided by 4 pi squared epsilon naught r times the, with a negative sign, times the integral of cosine of theta x hat plus sine of theta times y hat, okay, from 0 to pi. Okay, so let's do this integral. And so what we're going to see is that the integral of cosine is going to be sine. So this is going to be, I'm just going to look at this portion right now and then worry about the constant in the front later. So this is going to be sine of theta x hat evaluated from 0 to pi. So we actually see that this term is going to be 0 because sine of 0 is 0 and sine of pi is 0. And then this term is going to be a minus cosine. So this is a minus cosine of theta evaluated from 0 to pi. And so this is going to be minus cosine of pi is -1. Cosine of 0 is 1, but I have to subtract that, and so that's minus 1. And so this is going to give me ultimately a factor of +2. Okay. So in the end, when we're done with this calculation, we can see that this E vector is just going to be minus q divided by 2 pi squared epsilon naught r squared, capital R squared. Capital R squared time, I lost a squared here. I lost a squared. Times y hat. Okay. Now we see something kind of curious about this answer that we're getting, and that's the fact that this is only in the y hat direction. Now we could have come to the conclusion that this should only depend on y by looking at the symmetry of the distribution of charge. We know that this is a charge that's evenly spread over the arc of this circle. So that means that for every dq that I have on this side, that's going to create some electric field like this. I have another one on this side that's going to create an electric field like that. So when I add those two vectors together, they're going to cancel in x and only give me a vector in the y direction. Okay. You do an example where you have to split up quadrants because of the different r hat vectors. Let me think. Let me think. So I'm not sure if I want to do that because that's a little bit too much like the homework. But what I will say to make your lives a little bit easier, you can actually, as long as you're measuring theta from the positive x-axis, you can actually always say that r hat is equal to minus cos theta x hat minus sine of theta y hat. You can always say this. If what you're doing is you're measuring theta from the positive x-axis. But you don't have to measure theta from the positive x-axis. In fact, you could put it wherever you want. I could have defined this to be theta, in which case my r hat would have been, if this is what I'm saying positive theta is, this r hat would have been minus sine of theta y hat minus cosine of theta y hat. And then my limits of integration, instead of going from 0 to pi, they would go from pi over 2 to minus pi over 2. To clarify, split the integral from 0 to pi over 2 and pi over 2 to pi. Oh, yep, I lost my camera. Lost my camera. Yeah, I need to figure out. It doesn't usually do that. I don't know why it's doing it now. But in fact, I usually have, I wonder if this is why. I wonder if this is why. I usually have an SD card in it, and I don't right now because I'm uploading a video. Let me just make sure that that's done. Okay, yeah, that video is done being uploaded. So let's be experimentalists here and see if I have an SD card in here. Does that prevent it from doing that, even if I'm not recording? Okay, so hopefully that'll take care of it. Okay. Can I do an example when I split the integral from 0 to pi over 2 and pi over 2 to pi? Well, you don't have to do that. If what you end up doing is if you have I think I see what you're asking. If r hat is the same, you don't have to split these up. You could just do one integral over the entire interval. But if for whatever reason you decide, well, I want to define these angles a little bit differently, and then give me some different r hats. So let's say that I define this angle here and I define this angle here. So for this portion, the first r hat is going to point like this, and this is identically this. The second one is going to be plus. Let me think. Oh, this should have been an x to start with. The second r hat, if I wanted to do that, would be a plus sine of theta x hat, and then this would be a minus cosine of theta y hat. And then the limits for integration for this one would be 0 to pi over 2, and this actually would also be 0 to pi over 2. But I guess I don't know if I'm actually answering your question or not, Rachel. You should never have to split the integral from 0 to pi over 2 and then from pi over 2 to pi if you have the same charge distribution and you have the same r hat. You can always just do it as one integral. The only time where you would split your integral up is if you're defining the angles differently for the two regions, or if you're one of these weird people that likes to always have integrals like 0 to pi over 2, 0 to pi over 2, then that gives you a reason to want to do it like this. I don't think anybody would naturally say that I want to define the angle like this over here, I want to define the angle like this over here, and that's going to give me two different integrals. Yeah, so I'm not sure if that really answered your question. Or alternatively, for the split up, that would go from 0 to pi over 2 and then pi over 2 to pi. This would be 0 to pi over 2 and pi over 2 to pi. For this would be r hat is equal to minus cosine of theta x hat minus sine of theta y hat, and then this would be the same thing. But ultimately, whenever the argument of the integral is the same, this was something that I had mentioned briefly earlier because of something that somebody else had asked. Whenever the argument of the integral is the same, so if I'm integrating some f of x dx from a to b, and then I'm integrating it from b to c of the same function, you can really write, and if I want to add these two together, this is really the same thing as the integral from a to c of f of x dx. So I don't have to do the integral twice if I know that the argument of the integral is identical. Yeah, so hopefully that answers your question. In this example, the x component of the r hat changes as you move quadrants. Is the reason that it's accounted for in the overall integral because it's parameterized in terms of theta? Yes. So, and that's a good question, Brian. So what you're realizing here is, yeah, when I have the way that I drew this to start with, and when I'm writing this r hat is equal to minus cosine of theta x hat minus sine of theta y hat, this r hat is going to change so that it's going to point in the positive x when x is greater than pi. But we can see that this function actually does what we want if we plot our sine and cosine. So here's cosine, this here is sine from, this is pi over 2. This is pi over 2. This is pi. And we don't have to go further for this example. And this is cosine. Cosine goes like that. So this is pi over 2, and this is pi. So what we can see here is that for the interval from 0 to pi, sine is always positive. So whatever I plug in here for this, this is always going to give me a value that's positive, and then I multiply it by a negative. That's always going to give me something negative, which is what I need, right? Because when I look at this, the y component's negative on this side, the y component's negative on that side. So this sine, when I go from 0 to pi, needs to give me something that's going to be positive, and then multiplied by a negative gives me something that always points down. But let's see what happens with the cosine. The cosine's a little bit different, because what the cosine is going to do is it's going to be positive until I get to pi over 2, right? When it gets to pi over 2, it goes to 0, and then it goes negative. So for this whole region here, the cosine is going to be positive. I get here, it's 0, and then it goes negative. So that behavior of the cosine changing from positive to negative is accounted for in this r hat, so it does work over the entire interval. And again, this kind of goes back to what I was talking about with this example that we did before of how do I know that I have the right r when I said r was equal to the square root of a squared plus a plus y squared. How do I know that this is right? I can check endpoints. I can check to make sure that at this point it gives me what I know it should be. At that point it should give me what I know it should be in this point. I can do the exact same thing here. If I wanted to check and see, is this r hat the way that it should be? Well, we can consider what r hat's going to be at 0, pi over 2, and pi, and see, does this give me what it should be? So at theta is equal to 0, this is just going to be minus x hat, and then sine of 0 is 0. So r hat is minus x hat when theta is 0. Is that consistent with what we had? It should be, right? So this is going to point in the negative x hat direction. Let's see what happens when I plug in pi over 2. Pi over 2 in this, cosine of pi over 2 is 0, so there's no x term. Sine of pi over 2 is 1. There's a negative sign here, so this is minus y. So when I go to pi over 2, this should point directly down. And that is what we know it should be. Okay, let's see for pi. We go to pi. Cosine of pi is negative 1. Negative 1 times negative 1 is positive 1. So this gives me a positive x hat. So this points in this direction. And we know that sine of pi is 0. So yeah, I think that, again, I answered these in a little bit of a roundabout way. But yeah, Brian, that's a good question. And ultimately, the fact that the r hat's changing direction is taken into account for the way that I wrote this. Okay. And actually, if what you do is you always define theta from the positive x-axis, this will always be what r hat is, and all of the directions will be taken care of you because of the way that sine and cosine change directions as you change the angle. Yeah. Okay. So I think. So I'm going to try to make these an hour long until the final exam. But if there's like 1 or 2 last questions, I'll answer those. And then, like I said, I need to go back to writing the notes so that I can post those for you guys tonight. So I'll give you some time to type, and then I'll come back. My apartment's really hot, so I need some water. All right. Well, if you guys don't have any other questions, I'll shut it down. This will be posted, so you can watch it again later. And I'll see you guys tomorrow in recitation.